Greetings, friends. My name is John Gabriel, and this is the new Calculus channel. So, if you'll recall, in the previous video, we established the first three requirements from nothing, systematically from nothing. We basically used our reasoning processes and we formulated or derived this information of geometry systematically, beginning with only a void universe. It doesn't matter that we introduced parts into it to help us to explain the concepts, because an alien being with a similar intelligence, or just any sentient being, would have been able to do exactly the same. Okay, so these concepts exist outside of our minds. That's why they're called noumena. Noumena are perfect concepts. And so now that we've established the first three requirements, we're going to work our way to the fourth requirement, which is that all right angles are equal. So let's begin. So now, the fourth requirement requires the previous three. You can't get to the fourth. Now remember, everything comes from a circle. Parallel lines come from a circle. Yeah, that's right. I didn't make a mistake there, by the way. Sometimes I make mistakes, but I say things that I didn't really intend to. But yeah, parallel lines come from a circle. So do angles. So do triangles. Like you've seen, every triangle can have a circle going through all its 3 points. Okay, so even triangles come from circles. Now, to establish the fourth requirement, we need to have some other definitions in place, and the very first one I can think of, and which is the only one that we can get next, is the angle. So we have to define the angle. And then we also have to take note of the word symmetry, okay, which again is another Greek word which means having the same measure. When we say something has the same measure to another, when we say one magnitude has the same measure to another magnitude, it means that when we compare them, we end up with the same result. Okay, in other words, they're equal. Okay, so symmetry is the property or the attribute of being made up of exactly the same paths. Sorry, my breathing is a little belabored. Now, we also need to define what is an arc, and it's just any part of a circle's path. So if we have a circle like this, then this red is an arc and this blue is an arc, okay? And in fact, the whole circumference is an arc, right? So let's get back to my presentation, and we can see that the arcs, or the semicircular circumference path formed on either side of a circle's, we don't even have to see it. We can say they're equal because they're generated by the same radius. Okay, so coming back to this here, we can say that this semicircular arc on the top is the same as this one because it's generated by the distance is generated by the same radius, as you can see me doing here, okay? So now we define an angle primitively as the ratio. Now I'm still not using number there, by the way. Ratio has nothing to do with numbers at this point. We don't have numbers. So a ratio is only a comparison of two homogeneous quantities, sizes, or magnitudes. Okay, so in this case, we're defining the angle as the comparison of the arc length to the radius length. Okay, so that's what we're defining the angle to be. This ratio here. And by the way, this here would be a number, so angle is not strictly speaking equal to this here. It's equal to arc compared with radius. But later on, once we establish number, we're going to have this in the case where the angle has a measure. If it has no measure, then this here is really just a rational number approximation, okay? So that's very important to know, by the way. And we can see how to form this angle as follows. So we'll say it's the comparison of this red length to the length, the shortest distance, which is radius. So it's a comparison of this to this, right? Right, so this here would be what you call an angle, okay? All the way around an angle. And of course, at this point here, if we put in a grid, hang on a second here, if you put in a grid, this here would be exactly pi, the value of the magnitude pi. But again, remember, it's not a number. I'm sorry, that's pi over 2, not pi. This would be pi over 2, which is strictly speaking not a number, but a comparison of two magnitudes. All right, so that's what is an angle. Now, we don't care yet about the measure of arc or radius path because we do not have numbers. And even when we do have numbers, we can't measure most angles exactly. We can only measure them approximately, okay? And putting the symbol pi does not make it an exact measurement. Now, all that a ratio means is that these aliquot parts, arc and radius are aliquot parts, are being compared, okay? They're in a certain relation, and the result of this comparison is irrelevant for now, but we'll see later on how to arrive at a number or a rational number by comparing the arc length and the radius length quantitatively instead of qualitatively, as I'm doing right now without numbers, okay? So I mean, I can definitely compare this radius here, this circumference to this radius here, and I can tell you that it's longer right now because if I had to draw another straight line here, you'll see that it would exceed that value, okay? So I can qualitatively say certain things. I can't, it's not accurate, but it gives me a qualitative measure, not a quantitative measure. So now that we established that a circle's diameter partitions a circle, okay, because of symmetry. So we can call these here, this top arc and the bottom arc, semicircular arcs. And we know that the center partitions the diameter into equal radii, since any radius which is extended, remember, that's how we got the definition of a circle. We extended, to get the definition of the circle, we have to extend this radius to this radius so that it meets a circle again. If it doesn't meet the circle, then it's not a valid definition, as we saw in the previous video. So the radius from the center point of a diameter, which partitions a semicircle into symmetrical paths, is called a perpendicular, right? So we know that it will also partition the other semicircle into symmetrical paths. How do we know that? Well, consider that if we have a perpendicular like this and we start here, these two paths will be equal, right? These two arcs, because we are starting with a radius and we know that a circle is generated by the same radius, giving it the property of symmetry. All right, so if we have this perpendicular, then we'll know that all the arcs created by perpendicular to a diameter are equal, okay? And so that's why we call a perpendicular to the diameter the source of right angles. And so now we are ready to define any right angle as the ratio of an arc formed by the partitioning of a circle circumference into equal parts. Notice I did not say into 4 parts because we do not have number. I said into equal parts using only a diameter and its perpendicular. And so I've shown you now that all right angles are equal. And by the way, I call these equal angles here right angles, because this here is the only case where you have the property that all the angles are equal, okay? Given this scheme whereby we use the diameter and a perpendicular to the diameter. So we've derived right angle systematically, and we've established the first four requirements. And I don't have time to get into the fifth one, but even before we get to the fifth one, we're going to establish parallel line. And I'm going to let you think about that. I'll deal with that in the next part. But so far, we've established the first four requirements. And we're going to have to establish parallel lines as well before we get to the fifth postulate. So subscribe to my channel, click like. Remember that I'm being persecuted by the mainstream academia because I have exposed their ignorance on a grand scale. Academics don't like being told they are wrong. Okay, they don't like being shown their ignorance and stupidity. So yes, download my free ebook, become a subscriber, spread the news, all that good stuff, and study what I'm telling you right now. I'm John Gabriel, and this is the New Calculus channel. Till next time, friends, goodbye.